You guys are all good to this. How about stay up with Aaron? Aaron's coming to us from our platinum sponsor, TechnologyOne. They're responsible for the vast majority of the pizza that you guys and yeah, if you guys can give them a warm welcome.
I just want to say thank you, firstly, for having me here. It's actually a really great honour to speak to you guys. Speaking to students is really important to me. We have a lot of technology that runs our SaaS platform, and I want to talk to students who are really interested in running massive scale SaaS applications. Thank you for having me again. It's really much appreciated. My name's Aaron Hauk. I'm the head of SaaS platform at TechnologyOne. I look after the architecture for our networking and security mostly, but also dabble in storage, database, and automation as well. So, a couple of things. Firstly, my 40th birthday is coming up in a couple of weeks, and coming onto university campus makes me feel a bit edgy about that. So look out for the salty memes. Sorry about that. And the second thing is that the title of this presentation is a bit of a lie. We don't engineer for availability at TechnologyOne. Engineering for availability is what we used to do, and it revolved around these things. So I've been at TechnologyOne for about 15 years, so I've lived this evolution. We started out with a small IT team running all of our IT operations on our own data center, on our own servers and things like that. Now, the problem with servers is that they're very expensive. And that means buying them takes a long time because you've got to convince a lot of people to splash the cash. And because of that, you try and do as much with them as you can. And you pay people to keep them running. And your boss says pretty much if that server goes down, it better be because you're using it to look for another job. And that has big effects on the rest of your organisation. So you try and build redundancy into every component that keeps that server online. So you have redundant network interfaces, you have redundant storage, you have redundant hot swappable memory, and all of that costs a lot of money. And then that has another effect because you're so nervous about things going wrong and things failing that you try and avoid changing things, right? And so when the software team say we've got a new version of the software we want you to run, you go, oh, hang on a second, the old version hasn't crashed for like a week, and we really want to keep that going. And they're like, oh no, but there's these features we need, and so you take on change, but you do it really nervously, and it's all because you're really, really scared of failure. But that's probably not a great position to be in. Remember, we're not in the business of running servers, right? So why are we protecting the servers? We're in the business of, in our case, we write enterprise software, so software that runs other businesses. So we have to enable our company to be successful in that. They don't want to be successful in running servers. And so, despite all of this planning, and despite all of the redundancy we build into these servers, everything fails all the time. This is a quote from Werner Vogels, the CTO of Amazon Web Services. And it's kind of a bit sad, like he's the leader of one of the most profitable and successful IT companies going around today, and he's that pessimistic about the world. Everything fails all the time. But it's not sad. It's not really sad. It's the truth. Because we've all been saying it for a long time. Anything that can go wrong will go wrong. That's Murphy's Law. I'm sure you've all experienced it. You know, you're stressing, trying to get an assignment done, and then your computer crashes or you lose your file or whatever. That's Murphy's Law. And so we all have experienced failure. And in fact, that speaks to another truth that is even more universal. It's the second law of thermodynamics. You can't get more fundamental than that. Failure will happen. So don't avoid failure. Make failure part of what you do. Embrace failure. That's how you become successful. So we don't engineer for availability at TechnologyOne. We engineer for failure. And I'll talk about what that really is. But firstly, the thing that enabled us to change our thinking was back in 2011, the floods came down the Brisbane River. We had just moved to our new office at Fortitude Valley. We had a nice new shiny data centre, spent millions of dollars on this thing. And we had a redundant data centre down at 8 Mile Plains. And we hadn't really done a test on all of the systems, on all of the power delivery systems and things. And so that flood took out the cooling system that keeps the server room cool. And we had alarms that came out. My mobile phone started ringing, saying that the servers are getting over temperature. We need to do something about it. And our normal thing to do would be to start shutting down servers and failing them over to our other data center. But as the temperature rose in our building at HQ in the data center, one of the GBICs, one of it's a laser diode that sends light down a fiber optic cable. It overheated and melted. That particular one was the one that was connecting to our data center down at 8 Mile. We couldn't fail over. And so the business went out of business for 3 days. After all that money, after all that planning, we had redundant links, but both of them failed at the same time because both GBICs were sitting in the same rack with the same temperature variations, and they both just melted at the same time. So we decided to do something about it. We kind of came to the realization that we're not that great at running servers. So we should let professionals do it. And that's when we started our cloud migration, and now we're all in on AWS. So the advantage of cloud in the context of what I'm talking about is really that they've got more servers than you could ever want for, and they're available at an instant. API call, click of a mouse, you can get a server any size you want, GPUs, lots of storage, lots of memory, it's all there available for you to consume. And you only pay for what you use. So that already starts to lend itself to thinking about, well, do I really need all my servers all of the time? Or can I just turn some off at night or over the weekend? And these servers that AWS offer, they're reasonably reliable. I think they offer about 99.9 or 99.5 availability SLAs on their servers. So that means 99.5% of the time, those servers will work for you. But we used to engineer to a higher standard. We used to want our servers to be available all of the time, like 100% of the time. It's unachievable. Second law of thermodynamics says that. So there always has to be some downtime. So that was our first lesson. Never try and achieve 100% availability. It just doesn't work like that. And so the mind shift for cloud was that we could start focusing on our service rather than our servers. And that affected our whole business. So now we have access to a virtually unlimited number of servers, and we've got networks to connect them all, and you can start them with an API call. Let the servers fail. Like, just forget about it. Don't worry about it anymore. We have to start focusing on our product. So what do we have to do to convert our existing software into software as a service? Now, what I'm about to share with you can work with any application. Our application stack is .NET on Windows, but this I'm about to share with you works for, a Node.js server with a React front end running on Linux. It could work for any sort of programming language or environment you'd like to work with. So the first thing you need to do is log everything. Right, so failures are happening all the time, and if you're not logging it, you don't know what's going on. Okay? So, and you need to separate the need to capture what happened from the need to recover your system. Because recovery is your top priority. You make money when your systems are running. Right? So if you're spending time trolling through logs trying to work out what caused the failure, and your service isn't running, you're wasting money. So separate that. By sending your logs to a separate system, you're sending your A team to recover the system as quickly as possible, and then you can analyze the logs after the event and work out what happened. Now, we have our logging system for TechnologyOne SaaS is called Insights. It's a combination of Amazon Kinesis streams to accept all of the logged events. We use Elasticsearch clusters and Kibana to search and visualize that data, and then we store that data long-term in S3. We process about 1.5 gigabytes per minute through that logging system, which is about 11 billion events a day. That's a lot of data, and you can't process it all yourself. So the next thing you do after you log things is you automate the analysis and the response to logs. So if you see a logged event that tells you that a server has crashed, you might automate the replacement of that server. Or you might automate sending a message to the operator, the owner of that server, telling them about the failure. But automation is important. The next thing you'll want to do is configure some health checks. And the reason for that is you want to fail fast and fail often. And the idea of the health check is not to try and diagnose a problem. It's not to try and work out whether it was your disk filled up, or whether you got a virus, or whether a solar flare flipped a bit in your memory. If your application's not working, your health check fails. Alright? And it's as simple as that. So our health checks, the way we configure them, is we just hit our login page. Just do a simple HTTP GET on our login page. And if we don't see the word login in the response, that's a fail. Right? If it's a 404, if it's a 500 error, doesn't matter. It's a fail. And so there's only one thing you have to do when a health check fails. You smash your computer, you get a new one. It's quite simple. You don't have to think about it. Everything that happened will be in your logs. And if it isn't, it will be next time, right? Because you're going to think about it. So don't think about replacing your server, just do it. So as I mentioned, automation is everything. Automation is speed. And you want to fully automate server replacement when your health check fails. And to achieve that, you need to reduce the time it takes to launch a server. So the first thing thing you do is you'll pre-install your operating system and your application, and then you can capture an image of that pre-installed system. And the beauty of that image is you can stand up as many copies of it as you want, and you can stand it up in as many environments as you want. So we create these images, and then we have full duplicate environments of the exact replicas of our production environment that we can test them in safely, not affecting customer data, and that gives us our ability to do full integration testing, to test patching, to test the new features of the application in a very safe environment. And then, so once you've got this image, you can stand up servers based on that image, and they'll be exact copies of each other. So you'll need to provide those servers with some runtime configuration. So are they running in production, or are they running in test? Which customer is it for, or which database do I connect to? So you'll need a separate system, a separate configuration system to provide that information to your application. We've got a platform, we call it CSP, Cloud Services Platform, and its job is to provide runtime configuration to our environments, exactly as I said. Customers, databases, all those sorts of things. But we also use it to drive all of our other automation as well. So if I need a new version of our software deployed, I go into our CSP, I log in, and I hit deploy. CSP is based on our own CI Anyway software, so it looks and feels very much like the rest of our enterprise software. Now, actually, yes, the one thing to remember about your configuration service is it needs to be at least as reliable as your application. Right? So if your configuration service is dead, you might as well not have an application. So guess what? You need to monitor, you need to log, you need to make sure that your configuration service is available as well. In fact, we make our configuration service even more available than our application. The way we do that is we rely more on Amazon platform services to deliver configuration. And we do it with very simple technologies. So configuration data can be pushed into a DynamoDB table or into an S3 object store and then presented as a simple web service. Using all serverless components, we don't have to worry about patching operating systems or anything like that. And so we call those our tier 0 services. These are the services that must operate all of the time. And they operate globally as well. So we've got copies of all of the configuration data that runs out of AWS regions. So even if there's a complete failure that wipes out Sydney, where the AWS data center is, our configuration service will still run, even though most of our applications run in Sydney. Of course, if you're going to be destroying your servers all the time, you can't have your data on them. You can't have your users' data on them. So you need to separate your storage from your application. Now, AWS and other cloud providers offer a myriad of storage options for different types of data, whether it be SQL, relational databases, whether it be NoSQL, like DynamoDB, textual, like you put in Elasticsearch, graph databases for social networks. It's all just different types of data, and there's optimal ways to store and process that data. The advantage of using cloud platforms to do this is that it is really, really hard. Resilient storage is what I spend most of my time working on. Unfortunately, we can't use a lot of the Amazon platforms for our customer data, and so that's why I spend so much time on it. It's the same with files as well. File systems are really simple. you stand up a share on a file server and people just start using it, right? But if we're talking about systems that need to be really redundant and have to handle all kinds of failures, you've got to think about, well, what if the data center that that file server lives in catches fire? What do? I need another copy of all of that data. And how do I tell my application that that data is now over there? So it's a really complex problem. What we're moving to is putting our data on S3. Makes things a whole lot simpler. Amazon handled that resiliency and that redundancy for you. And they can offer SLAs far in advance of what we can do. So there are other types of failures that you have to think about. So failures of scale are something you're going to have to think about as well. There's lots of different ways that your application can require scaling. It can get busy. You might have gone viral. You might have a business process that you have to handle. Like we run student management applications, so at the beginning of every year, we have to handle the enrollment of hundreds of thousands of students on our SaaS platform. And they're all logging in, they're all trying to pick the best classes in the times that mean they can get the most sleep and all of that sort of thing. That's a really busy time of the year for us. And so we have to scale our servers out really wide. Now, in simpler times, you might have thought, well, why don't I just get a bigger server? I mean, I'm on the cloud, I can just click and get a bigger server, right? But a bigger server still has hard limitations that are just unavoidable. The number of connections it can accept, the operating system might not be able to address more memory than the big servers you can get on AWS. So you have to scale horizontally, and scaling horizontally gives you a whole lot of other benefits as well. So a single server failure doesn't have to affect your whole application. I'll talk a bit more about that later. But to scale horizontally, you need to solve three problems. Firstly, you need to automatically scale based on load. And that means scaling out and scaling back in again, because you need to optimize the cost as well. So to scale based on load, you need to find a metric that accurately measures your load. Now that can be something simple like CPU, but often it's not that simple. For web applications, it might be the number of in-flight requests. It might be memory, it might be network, it might be anything else that you decide is important to your application. But you've got to pick that metric and then decide what the scaling points are. When it reaches this threshold, am I going to add more servers? How many servers am I going to add when that happens? And then when it falls below this other threshold, how many servers am I going to take away? And when can I do that? Because if there's users connected to that server, I can't just kick them off. I need to wait for all those transactions to finish. Thankfully, any good cloud provider will give you a service that does this. So Amazon have auto-scaling groups that can take care of this for you. You just got to feed it a metric and how many servers you would like to add or remove in any scaling unit. The next thing you need to solve is load balancing. We've got all these servers, you need to get all of your users talking to those servers. So how do you do that? And that depends strongly on your application as well. So if you've got a stateful application where users need to do long transactions involving a single server, or where multiple transactions need to coordinate with each other, you might need to send each user's traffic to an individual server. So you'll have different load balancing algorithms depending on the nature of your application. For simple web applications, it's much easier, and I'd strongly encourage you to go down that road. So whenever you've got state, whenever you're storing bits of information that need to be coordinated between transactions, store them on a separate data store, and then you can randomly allocate those transactions to any server in your fleet. Again, your cloud server should provide a load balancer for you. Amazon provide application load balancers for web applications. They handle things like SSL. You can do authentication. You can decide whether you're going to use sticky sessions so that users keep using the same server over again. Lots of things to think about there. And now the third problem is even more difficult. You need to be responding to real user traffic. So now we're scaling in and out. We're paying more when we're busy. That's a good thing. But if we're getting a denial of service attack, if someone's smashing our website, trying to break it, I don't really want to pay for that traffic. And I don't really want to pay for all those servers that I'm going to need to keep our application online for our real customers. And so we're going to lean on our cloud platform to give us that capability. Amazon can handle a bit more traffic than we can afford. The last I looked, they were handling DDoS events in the order of terabit per second. My biggest network connection is only 10 gigs, so I'm gone if that hits us directly, right? So we have to leverage AWS to help us filter that traffic. So there's two things we can do. Firstly, use a CDN, a content delivery network, to host your application. CDN is like Cloudflare, or CloudFront is Amazon's equivalent. And the way it works is they've got web servers all around the world, in lots of different locations. And you route your website through their CDN. When a request comes from a particular region, and it's got some static content like images or static data, the CDN will cache that data as close to that user as possible. So when his neighbor or when her neighbor comes and makes the same request, it gets served from the CDN cache. It doesn't go back to your application server. You don't even see that traffic. And if you think about that on the scale of hundreds of thousands of users, that's a lot of application traffic that you don't have to handle. And that means you don't have to scale as much. You're not paying as much for that traffic. And then the other component that you need to think about there is web application firewalls. A web application firewall is a piece of infrastructure that looks at the nature of a web request and decides whether it should let through or not. And it could be a decision based on the geographic location of the calling user. It could be a decision based on what browser they're using. It could be a decision based on whether they've got a SQL injection in a form post. Right? Let Amazon block that for you. Because they can handle all of that traffic. And if they're filtering it, we're not paying for all those servers to handle it. So we've got a nice robust fail and failure, but we need to handle things in our application as well. So we need to help design our application to handle failure as well. So as I've been saying, small, fast transactions, handle them synchronously. That's what HTTP does for you. Web applications are brilliant for that. But not all transactions are like that. Some transactions you might find like processing big data, doing a report, whatever, they'll take minutes, sometimes hours to process. So you need to handle those sorts of transactions asynchronously. You can't have your user sitting there on their browser waiting for the response to come back. So you accept the request, you process it, and then you send a message back to the user to say the job's done. We do this in our software. We've got a process, or we've got a service we call our DP server, the service, distributed processing. And it's quite simple actually. The request comes in from the application server, says, hey, this user wants to run a report or wants to do some sort of analysis on their data. And that's all that goes into a job definition. Who the user is, what they need to act, or what job they need to run, and that simple message just goes into a queue. The queue is run by AWS. It uses SQS. And then we have a pool of servers that just pick jobs off the bottom of the queue and process them. And we can scale that pool of servers as big or small as we want, depending on how fast we want the jobs in the queue to be processed. So by using this simple architecture, we've taken something that can be very painful for users and made it much more reliable. Imagine running a report, it takes 3 hours to process it, and then at hour 2.5, you get a message saying that the server crashed. That'd be really frustrating for your users, right? So in our case, if the server that's processing that report crashes, the job doesn't get deleted from the queue. So another server will pick it up and start it again. Now it'll take a long time for that job to finish, but it will finish. So the other part is to use smaller, more specialized servers. Our application was traditionally delivered on a DVD. If you guys know what that is. So we used to ship the software to our customers. They would install it on their own servers. They had their own database infrastructure and everything. What that meant was we couldn't really give them a complex install. Like we couldn't say, well, you need a database server of this type, you need one of that type, you need a server for this, you need an auto-scaling thing, you need a load balance. We couldn't put that on our customers. A lot of our customers are small city councils or small not-for-profit organisations that can't afford lots of infrastructure to run our software. So it was really simple. We called it's a monolithic architecture, is what we called it. Everything was all in one box, and if that box failed, well, that was something our customers had to worry about. But on cloud, we've got this big sprawling network of infrastructure we can take advantage of. And so instead of having a big monolithic architecture, we can start to break our application up into small pieces based on their functionality. And so we started by taking common functions. So going back to the student example, so all of the functions that are involved in enrolling a student, we'll run them on one type of server. And we'll scale that independently of all of the other servers in our fleet. Right, so when enrollment time comes around, we only have to scale one part of our infrastructure. That means we can be more cost effective. And it means we're putting less stress on the underlying databases and things as well. So we call that a cell architecture. Currently run around 20 cells in our enterprise application. So there's 20 different functional groups of independently scaling servers that we run. And in some cases we go even further and we just break it right down to a single function that runs in its own scaling group. That's the definition of a microservice. So that's how you evolve a monolith to a microservice. The benefit of all this is that it gives us this awesome experience called graceful degradation. It means that one part of the app might fail, but the rest of the app will keep running. And even when that one part does fail, a simple retry on the request will get a good result. So it changes the user's perception from, oh my God, the cloud's gone down, to, oh, that took a little bit longer than usual. That's okay. I can get on with my job. So you've got to build that logic into your application as well, that retry logic. So when a request comes back saying it failed, know that the server that served that bad request might be having a bad time, but you've got plenty of other servers there that can handle it. So just resend the request. And you've got to design your application to be able to do that. Here's some memes for you. So this is where the fun bit happens. You've built this awesome SaaS platform. Now you get to break it. And that's actually a really important part of what we do. The only way that you know your application will be resilient when bad things happen is if you test it. And you've got to test it all the time. So yeah, don't wait for the second law of thermodynamics to kick in. You can be the instigator of your own chaos. Netflix have a suite of tools that do this automatically for you on AWS. They call it the Chaos Monkey. And the Chaos Monkey's job is simply to pick a random server and turn it off. And you run that in production. So that in my past life, that would have been stupid. You wouldn't do it because you just go and get another job if someone was doing it, right? Letting a chaos monkey loose in your server room. But that's exactly what we do. In fact, that's how we do our patching. So instead of waiting for Windows updates to kick in, get the latest security features, kill the servers. All of our servers get killed every 30 days. And they get replaced with servers with new images that have already been patched. Patch management. Done. Yeah, so randomly break production for fun. On the Chaos Monkey, actually, Netflix have other tools that they call Chaos Gorilla, which breaks entire data centers, and Chaos Comp, which breaks entire regions. They run that in production. So whenever you're streaming your movies or TV shows, you won't even notice it. But every now and then, they'll be the server that's streaming your video will fail. It's amazing. It's brilliant technology. Okay. So there's a lot more that I'm not talking about. I could go on and on and on, but I don't want to bore you. But there are so many aspects to what we do in our SaaS platform. And it's all around engineering for failure. So just to reiterate, some simple steps to SaaS. Firstly, log everything. If you're not capturing it in your logs, you're not going to know what went wrong. And your priority is to get things up and running, so you don't want to waste time on that. You need to engineer some simple health checks. Just a simple HTTP get on your front door. Simple. You need to fail fast and often. Automate everything. Automation is what we do for a living. Separate your data, your application from your data and the storage systems. Scale horizontally. Design your application for scale and inject your own chaos. If you're after a little bit more reading, here's a couple of things for you. Google are obviously the masters at running applications at scale. So if you want to learn about that, go to Google, search for SRE, Site Reliability Engineering. I got to meet the guys that wrote the textbooks that go along with this. These guys are on another planet. They are amazing. and I had a 30-minute conversation with them, and I learned more in that 30 minutes than I've learned in a lifetime. The Phoenix project. I got into trouble for, I listened to this one as an audio book, and my girlfriend was like, why are you listening to a book about your work? But again, this was a really interesting one because it didn't really occur to me until I read the book. Well, I heard the book. It talks about how some of those principles I just talked about small units of work and all that, they're ideas that were borrowed from the automotive industry. This is how Henry Ford started to build production lines. It's really, really mind-twisting stuff when you think about it, but it's so true. I highly recommend having a read of that one. And then finally, of course, as I was saying, the Netflix tech blog. You think a few years ago that company was sending DVDs in the mail, and now they're one of the biggest tech companies in the world. So read about how they do it as well. So that wraps me up. Thank you for listening to my talk. And if breaking things and failing is something that you might be interested in, come and talk to us. We're doing a game day next Wednesday night, where you get to compete with the guys from QUT. We've got a whole bunch of games lined up for you. It's great fun. There'll be food, there'll be beer, there'll be games. Please come along to that. Secondly, go to our careers website. Our grad program enrolments will be starting very soon. So check out our careers website if you're interested in coming to work for us. And that wraps me up, so thank you very much for your time.